Industrial machines operating on pure Boolean logic don't hesitate. When a true command is issued, mechanical presses and robotic arms slam into position instantly. But controlling physical forces often requires pacing. That is the core function of a PLC timer, artificially delaying a signal's transition, whether that signal is turning on or turning off, within a ladder diagram. In an environment like Studio 5000 Logix Designer, these timing instructions dictate exactly when real-world actions are permitted to happen. Success in this environment involves managing three distinct parameters: the Boolean conditions that trigger the timer, the mechanics of how it accumulates time, and whether its memory is volatile or retentive. Evaluating deterministic scan cycles, the PLC timer functions as a dedicated memory structure that gates physical industrial events. Every timer instruction in a PLC relies on a specific memory allocation called a backing tag. This block represents a timer's memory structure, and the first configurable parameter inside it is the or preset member. The programmer defines this variable as the absolute target time limit for the instruction. It remains static. Beneath it is the ACC, or accumulated member. This variable dynamically tracks the passing time. As long as the timer remains actively enabled, the PLC updates the ACC value during every single scan cycle. These two numbers dictate the output. The moment the accumulated value reaches the preset limit, a separate Boolean done bit transitions from 0 to 1. All timer instructions in Studio 5000 manipulate these three specific tags. The only variables are the exact conditions that trigger the count and how the timer clears its memory. The most common configuration is the timer on delay, or TON instruction. Its primary purpose is to delay a signal from turning on. This is a timing diagram mapping a TON's behavior. The process starts when the rung-in condition, the logical trigger feeding the timer, becomes true. Once the rung goes high, the timer immediately begins accumulating time, represented by this rising graph heading toward the target pre-limit. When the accumulated time equals the preset time, the timer is done, and the output bit turns on. But this instruction has a strict volatility rule. If the run condition drops to false at any point, all progress is wiped, the ACC zeroes out, and the done bit drops. We classify the TON as a non-retentive instruction. Any loss of run continuity clears the memory instantly. The TON is a strict gatekeeper. It forces an input condition to remain continuously true for a defined duration before allowing the signal to propagate. The logical inverse of that gatekeeper is the timer off delay, or TOF instruction, which delays a signal from turning off. Looking at a new timing diagram, we see a crucial distinction. The TOF only begins its work when the rung condition goes false. When the instruction loses its signal, it becomes enabled. The accumulated value starts tracking the elapsed time only in the absence of a true input. When that elapsed time hits the preset threshold, the timer completes its cycle and forces the done bit false. If the rung condition rises back to true, the instruction is no longer enabled. The accumulated time is reset to 0, and the done bit immediately returns to a true state. Despite relying on a false state trigger to count time, the TOF shares the identical memory vulnerability as the TON. It is entirely non-retentive. Volatile timers work perfectly for continuous signals, but if you need to measure a cumulative event across multiple interrupted cycles, a non-retentive timer will simply keep resetting to 0 and fail. This chart shows how the retentive timer on, or RTO instruction, solves the problem of a staggered input signal. While the TON on the left resets at every interruption, failing to reach the target, the RTO on the right simply pauses. When the signal drops, the accumulated value flatlines. When the signal returns, it picks up exactly where it left off. The accumulated value is indefinitely retained across multiple pulses. It will continuously increment until it finally crosses the preset threshold and turns the done bit on. But retentive memory requires external intervention to clear. The instruction stops counting when it hits the limit, but it will not automatically reset when the run goes false. To clear the accumulated value for a new cycle, you must program a dedicated reset, or RES instruction, targeting that specific timer's tag. This behavior makes the RTO ideal for tracking totalized physical events, like monitoring cumulative running time of a motor to determine when maintenance is required. The RTO handles temporal fragmentation by completely separating the trigger condition from the memory reset condition. Architecting precise timing in a PLC depends entirely on selecting the proper instruction for the exact state manipulation you need. This matrix lays out the rules. The TON requires a true enable state and volatile memory. The TOF uses a false enable trigger, but is equally volatile. The RTO uses a true enable trigger with retentive memory, demanding a dedicated reset instruction to clear its data. It is important to note that these specific state behaviors and triggers strictly govern the ladder diagram programming language within Studio 5000 Logix Designer. If you write logic in other environments, like function block diagrams, you will encounter these exact same timing concepts, but the instructions will execute with slight behavioral differences. Industrial systems operate on the rigid timeline dictated by the controller. Mastering these three distinct memory manipulations ensures that the deterministic events on the factory floor unfold exactly when you need them to.